Aloha, my name is Robert from Neapapa, and welcome to the Online Professional Development for Module 12 of the Canoe project. As always, we begin by logging into our website, www.stemd2.com, and after we've logged in, let's go on to Students, and let's build a canoe. Module 12 is in Unit 5 of the Go Math book, so let's go down to Unit 5. From here, we can go down and click on Module 12. Here are the list of activities for Module 12, which is about the Pythagorean theorem. The first activity that we'll be discussing is Canoe 12.1.1. This is the activity that corresponds with Lesson 12.1 in the Go Math book. In this activity, we will try to buy some material for a sale. The store that we're at does not price their sales linearly. So for example, if you want a sale that is twice as big, it does not cost twice as much. So as we can see here, the 4x4 sale is 4 times bigger than the 2x2 sale. However, it is 8 times more expensive. If we go down, we can see that the 10x10 sale is 100 times bigger than the 1x1 sale, but it's 1,000 times more expensive. In this activity, we need to obtain 25 square feet of material. But we have two options to do this. And the first question will ask you to compare the two options. The first option is to get a piece that is 5 feet long and 5 feet wide. In the second option, we need to get two pieces. The first piece has to be 3x3, and the second piece has to be 4x4. And then we need to find a way to cut these two pieces and sew them back together to get a 5x5 piece. After we've discussed this problem, we will conclude this activity with a hands-on proof of the Pythagorean theorem. In the hands-on proof of the Pythagorean theorem, we will need 2 square sheets of paper. One sheet will have sides of length A, and the other sheet will have sides of length B. A and B can be whatever they want, but the effect is more dramatic when A and B are different sizes. With these square pieces of paper, we will cut them up and then we will tape them back together into one bigger square. The final square will have sides of length C, where C is the length of the hypotenuse that you get from an ABC right triangle. This proof will always work no matter what A and B you choose in the beginning. In this video, I'll walk the students through the proof from the beginning to the end. We recommend following this activity as it is, or turning this activity into a challenge. So for example, you can have the students cut up squares and then trade the squares with each other, and then try to find a way to cut those squares up and then put them back together into one bigger square. And then you can show this video after they've had a chance to try it on their own. Okay, welcome back. The next activity that we'll be talking about is Canoe 12.3.1. In this activity, we will be revisiting an activity from Module 1. So we will be talking about the haleba'a, which is the house of the canoe, also known as a place where the canoe is stored and built. The haleba'a in this activity is 9 feet wide and 9 feet long, and we want to know what is the longest canoe you can fit in this haleba'a. Well, it turns out to be the length of this diagonal, and with the Pythagorean theorem, we can find out this length. Of course, houses are 3-dimensional objects, so let's take a look into the third dimension. Here's a 3D picture of a haleba'a that is 9 feet wide, 9 feet long, and 9 feet tall. It turns out that we can fit a longer canoe if we lift one of the corners up to the ceiling. So in this question, we want to know how long is this canoe. It's actually a little bit tricky because we need to use the Pythagorean theorem twice. First, we use the Pythagorean theorem to find the length of this shadow, using the shadow and these two edges. And then we use the theorem again to find the length of the canoe, using the canoe, this edge, and the shadow. Now let us generalize this. Instead of a haleba'a of a width, length, and height of 9 feet, let's consider another haleba'a. This one will have a width of A, a length of B, and a height of C. With these new variables, we can use the same strategy as last time to find the length of this canoe, and we'll call this length D. We can compare this new equation with the equations that are in the Pythagorean theorem. It turns out that the square root of a squared plus b squared, which we got from the Pythagorean theorem and we used to get the length of this canoe, is actually called the two-dimensional Euclidean distance. Also, the equation for the length of this canoe is called the three-dimensional Euclidean distance. In the final question, we ask the students to think about what this actually means. So why is this length the two-dimensional Euclidean distance? And why is this length the three-dimensional Euclidean distance? We also want the students to try to imagine what a 4, 5, or a 6-dimensional Euclidean distance means. In fact, what is a dimension? This is actually a pretty hard question that most college students do not understand. So please tell your students not to stress about it, just to use their imagination and to articulate their logic. That's it for this activity. It's actually one of the hardest activities that we have, but it's one of my favorites. And it's also one of the first activities to ever touch on theoretical mathematics. Please pause the video and take some time to review and reflect on it. Let us know what you think, and let us know how you can use this activity in your classroom. Alright, welcome back. The final activity that we'll be looking at is Canoe 12.C.1. In this activity, we will be applying the Pythagorean theorem to get from one place to the other. So right now we have a canoe that has been damaged by a storm. This canoe can go 6 miles at a time before it sinks. Here is a map that tells us where we are, where we want to be, and the islands that are all around us. And what we want to do is find a path from here to here by hopping on these islands. Remember, we can only go 6 miles at a time, so we have to be careful to make sure that any two consecutive islands are not more than 6 miles apart. We ask the students to describe their path using a sequence of ordered pairs, just like in this example. That was a pretty straightforward activity. Please pause the video and take some time to check it out. Well, that's it for Module 12. We'll see you again soon for Module 13.